argon age. And the samarium neodymium age is more than 3 times the potassium argon age at 1588 million years. How can it be that these 3 methods can give such wildly different ages? And the potassium argon single sample ages varied from 577 million years up to over 1 billion years. See, no 2 methods agreed. No 2 methods agreed. Now, when we plot these, that's where they sit. Now, notice something interesting here. Where we've got the rubidium and strontium, the rubidium and potassium, notice that the potassium decays faster. It has a present rate of decay which is faster than rubidium, and it gives a younger age. In fact, in every result we obtain in any rock unit, the potassium age was always younger than the rubidium age. Now, one thing I didn't mention before is that potassium and argon decay in a different mode to uranium and samarium. Uranium and samarium decay by what we call alpha decay, whereas potassium and rubidium decay according to a beta decay process. It's a slightly different type of radioactive decay. Notice, both in this diagram and the last diagram like this, and I'll show it to you again shortly, the alpha decay ages are always older than the beta decay ages. That's interesting. We actually started to see a pattern emerge in these results. So if you don't believe it, let's have a look at another example. Let's go to where the molten lava coming up from the mantle didn't make it all the way to the surface to explode as a volcano. Its progress was impeded, and it was forced out. It hit a rock layer and then moved out horizontally, so it was squeezed like toothpaste between the rock layers and cooled under the ground. We call that a diabase sill. And here's an example in the canyon. You see that black rock there, not down at river level, but beneath that white streaky material, sloping up towards the skyline. That's a diabase sill, where the basalt rock, it was squeezed, when it was molten, was pushed sideways instead of going out through the top of a volcano. And here's another example in the further downstream of another one of these diabase sills, and we've actually put lines there to illustrate. This is nearly 300 feet thick. We actually collected a series of 11 samples from top to bottom because the composition of the rock changed as you went through that sill. And that's ideal for isochron dating because you've got to have a variation in composition. So what kind of results did we obtain for this diabase sill at Bass Rapids in the Grand Canyon? It gave a potassium argon isochron age of 841 million years, a rubidium strontium isochron age of 1,060 million years, and it gave a samarium neodymium isochron age of 1,379 million years. By the way, we even took a single sample, separated it into its constituent minerals, and analysed each of the minerals to plot on a line, because that's an even more superior type of radioactive dating method. And then the lead isochron age was 1,250 million years. The model ages of potassium argon model ages varied from 656 million years to over 1 billion years. So when we plot these results on the same diagram, notice again the alpha decay ages are older than the beta decay ages. The uranium and samarium ages are older than the potassium and rubidium ages. And again, the potassium age is younger than the rubidium age. The uranium age is younger than the samarium age. The faster the decay rate today, the younger the age. The slower the decay rate today, the older the age. Isn't that interesting? We saw a pattern in these results which gives us a clue that there's something systematically happening here to cause these different ages? Well, one last example. One of the granites in the Grand Canyon, the Ells Chasm granodiorite. And this is one of the Ells Chasm granodiorite there, that grey rock. It gave a rubidium strontium isochron age of just over 1,500 million years, samarium neodymium age of over 1,600 years, and a lead-lead age of nearly 2 billion years. The error margins are a bit larger with this rock, and so the overlap, there's a little bit of overlap, but still the pattern is there, except in this instance, the uranium age is older than the samarium age. But some of the labels are in the wrong place there. The rubidium age, those should be up higher. The rubidium age is still younger than the samarium and the uranium. So let's try and, well, I've got one more example here. Somerset Dam. It's where the basalt magma, and this actually comes from where I live on Australia's east coast. Brisbane, city of Brisbane, about 1.5 million people. And Somerset Dam is actually one of the water supply dams for the city of Brisbane. And there's a place there where the molten rock has cooled under the ground in a larger mass of rock. And it's actually layered with different varieties of this original rock. And there's Snelling, one of the Snelling juniors that was helping me on a field trip. Okay. We get a potassium argon isochron age of 174 million years, a rubidium strontium age of 393 million years, and a samarium neodymium age of 259 million years. A lead-lead isochron age of 1425 million years. Again, different methods on the same rocks giving you widely varying ages. Okay, let's sum up. But shouldn't the different methods on the same rock yield the same age? I mean, that's what the textbooks say. They're all clocks that are supposed to measure the true ages of these rocks. Yes, if the three assumptions are correct.